This will be a quick review of Exit Slip 2 on composition of functions. So you've already tried these problems for yourself. Let's just compare and see how we did. So we're going to find f of g of x and g of f of x, as well as the respective domains. So to begin, we're going to find f of g of x. And in talking with some of you all, a good way to handle this to begin with is just to immediately replace g of x with its equivalent expression. So notice in this problem we're told that g of x is equal to the square root of x. So I'll insert the square root of x when I see g of x. So now it starts to feel a little bit more specific. Now we're finding f of the square root of x. And what that's really saying is now we need to evaluate function f at an input of the square root of x. So here is our function f. When we input x, we get 5 minus the input of x squared. So if we're inputting the square root of x, we get 5 minus, and then we insert the input of square root x, and then that's being squared. So that is f of g of x. I'd encourage you to take one last step just to simplify. We can see here that when we square a square root, we're left with just the quantity under the radical. So I'll just end by saying f of g of x in its simplified form is equal to 5 minus x. So really either of these answers would be just fine. Turns out that the non-simplified answer is a little bit more helpful for finding the domain of the composition of functions that we just found, because the square root of x has a restriction of x being greater than or equal to 0. So when we think about the domain for f of g of x, the domain for f of g of x will be the values in the domain of g for which g of x is in the domain of f. So if we stop and think about it, the domain for this square root function, g, is all x. I can write it a couple ways, such that x is greater than or equal to 0. That's our set builder notation there. Or in interval notation, it would just be from 0 to infinity. So turns out all of those values work out just fine for 5 minus x, which is a linear function. So the domain for f of g of x is thus all values of x such that x is greater than or equal to 0, so that we satisfy the restriction on the radical. Or again, the interval notation for that would be 0 to infinity. So as long as you have one of these two answers for domain, you're in good shape. And I do agree, if you're thinking, this is kind of weird, domain for composition is not the most intuitive, because we have to consider both functions f and g. Alrighty, so hopefully that's seeming pretty good. Let me know if not, but I'm going to go ahead and do part C and D, where we're finding g of f of x. So we hopefully pretty successfully found f of g and its domain. Now we're working g of f of x. So let's begin the same way. I'm going to begin by saying anytime I see function f, I'm going to insert what I know it's equal to, right? So f of x is equivalent to 5 minus x squared. That becomes the input for g. And function g says, right, the rule of this function is whatever you input, make sure you square root it. So I'm simply going to square root the 5 minus x squared. And in this case, that does not simplify further. I know it can be tempting to say that this is equal to something like square root of 5 minus x, but we can't break down radicals in that way when there's addition or subtraction. Only if it were like product could we do a little bit more work there. So just a big caution with that, easy to do, not equivalent. So we're going to stop at the step before. And I'll just rewrite that so we all agree on the final. So g of f of x is equal to the square root of 5 minus x squared. Okay, before I find the domain, we'll do that. Just want to offer maybe one more thought about functions, right? We've talked a lot about functions as input-output machines. So if it helps your thought process, you could even write function g, for example, as g of, and I'm just using a little empty box, g of some quantity is equal to the square root of that quantity. That's kind of a more generic description of function g. So when we're doing a composition here, right, when we did g of 5 minus x squared, that 5 minus x squared filled in my little empty box. So we can evaluate that function at different inputs. In the example here, it was evaluated at an input of 5 minus x squared. So just food for thought, lots of different ways to think through composition. So if one of the ways we've talked about isn't clicking, just holler and we can talk about some other ways. Now we've got to find the domain. So g of f of x is a radical function, and f of x had no restrictions, right? F of x involves a quadratic, and quadratics have domain of all real numbers. So really the restriction is on that square root. And the thing about square roots is we want to make sure all values under the square roots are greater than or equal to 0. And that ensures that the output is thus a real number. So remember, for example, that something like the square root of -4 is imaginary, right? So it's not a real number. And we'll see those later on in the course as well. So for the purpose of our domain, we will simply snag the stuff underneath the radical and say, hey, that stuff there needs to be greater than or equal to 0. And then we'll just solve that inequality to find what values are okay. This inequality is a little strange. I'm going to go ahead and add x squared to both sides. And then typically what I do when I get to this point in an inequality is I consider the corresponding equation. You can do it many different ways, but I just consider x squared equals 5. So I flipped around the 5 and the x squared. And if I was asking how do you get x alone, you guys would tell me we've got a square root both sides, right, to undo x squared. And this is our square root property. Technically speaking, we get back actually a plus or minus the square root of 5, right? And that's because a negative square root of 5 times a negative square root of 5 would be 5, and then a positive square root of 5 times a positive square root of 5 would be 5. So we need the plus or minus. And what that tells me, again, this is just one approach to solving with inequalities, and we'll see more of this when we have absolute values. We do some work with absolute value inequalities too. So I'm just going to place the negative square root of 5 and the positive square root of 5 on a number line. And I'm going to pick a value that's clearly in one of those intervals, right? So basically we just created 1, 2, 3 possible intervals. And the deal with these guys is it's either going to be true that the domain values we care about are like the outsides of this interval, those outer pieces, or it could be true that we want the inside values. So an easy way to check on that is to pick a test value. So I know a good number in between negative square root 5 and positive square root 5 is 0. So I just test x equals 0 by plugging 0 back into the inequality. So if I plug in 0, I would get 5 minus 0 squared. And I'm asking myself, is it true or false that the left side of the inequality is greater than or equal to 0? So 0 squared is just 0, so my statement becomes 5 is greater than or equal to 0, and that's a true statement. So we want the values that are true. That means the solution to our inequality is all values between and including the positive and the negative square root of 5. Oops. Sorry about that. There it is. So we want this space here. So again, kind of crazy domain problem there, not the easiest, But the domain could be expressed in interval notation as the closed interval from negative square root of 5 to positive square root of 5. It's a closed interval, meaning we use brackets rather than parentheses because the inequality was or equal to, right? So as a very brief aside, if you have, I'll make a little bit more space, a greater than or a less than, these are scenarios that would result in parentheses. If you had a greater than or equal to or less than or equal to, those are scenarios that would involve brackets. And piecewise functions, which is another thing we've looked at, that could translate to open circles on a graph when it's strictly less than or strictly greater than, and it would translate to closed points on a graph if it was greater than or equal to or less than or equal to. So there's the domain. Interval notation looks pretty nice, I think, for this one. If you prefer set builder, we could still do that though. We could say all x are good such that x is bounded between and including negative square root 5 and positive square root 5. So either of those notations would be great for the domain. Whew. All right, not the easiest problems. I think the homework will feel a little easier than that. So hope that helps. Let me know what questions you have.